So our next presentation is going to be from team 22105 Runtime Terror, who are actually based in San Diego, California. And at the Michiana premiere event, they were the Inspire Award third place winners and finalists aligned first pick of their division. They also won the Think Award second place at the San Diego Championship. And they'll be talking about custom Boxtube extension in FTC. Here. Okay. Um,
Hi. Hi. I'm Rahul, and I'm part of Team T2105, and I'm here with my teammate Kanishka, and we're gonna be presenting about custom box cube extension in FTC. So, first of all, what is Boxtube? So, Boxtube has kind of increased in popularity in FTC over the last like year or so, and it's an alternative to linear drawer slides. And it was kind of first started off in FTC by Team 16379 CookieBots, and it has a lot of benefits, such as being compact, rigid, and a lot lighter than standard aluminum linear slides like Misumi's. But it has a lot of difficulties that come with using Boxview because it has to be fully custom implemented, which can make it a challenging mechanism for many teams. And that's why we're hoping this presentation can help alleviate that. So, starting with like the pivot superstructure of Boxtube. So, first of all, in this presentation, we're going to be mostly covering the like hardware side of Boxview. So its Boxview is best used in pivot archetypes, which means that in a pivoting structure like similar to the team Jack in the Bot in FRC, and that allows you to horizontally extend and vertically extend. Now, when you're designing Boxcube in a pivoting structure, it's really important to have the extension and pivot be coaxial, which means that the extension motor should be placed off of the pivot, like rigidly mounted to your robot, and that significantly reduces the amount of weight that's pivoting, which will increase your cycle times. So there's many ways to achieve like a coaxial system like this. The way our team went about this is our pivot structure is done by these 32 millimeter Go tubes from GoBuilda, and with clamping mounts and pulleys for them. And then our extension is on a 8-rex shaft that goes through the center of all of these Go tubes, with the spool being here. So in these diagrams, you can kind of see that we have the motor, which is belted up to this central shaft, and then the pivot motors pivot around these aluminum tubing interfaces. Now, there's different ways you can accomplish this. You can use an offset gear, like to achieve this coaxial system. But in general, however way you want to do this, you doing this will definitely reduce the weight of your pivot. Now, in terms of ratios, the ratio our team used was 1400 RPM on the extension with two motors and 83 RPM on the pivot with two motors. Now, you should independently calculate their optimal ratio depending on the weight of your system in CAD. And also for pivot, you don't have to use two motors. You can also do one motor, but you should probably aim for a slightly lower RPM of around 60 RPM. Now, another key important for general pivot system is that you want to reduce the backlash in the pivot. So if you don't know what backlash is essentially like play in the pivot without moving the motor. And this can be caused through many factors. So first of all, the number one thing to reduce backlash, I'd say, is to have hard stops at your intake and outtake positions. So for this year, for example, when you're scoring at the bucket, we have this hard stop you can kind of see here with a 12-rex shaft that hard stops the box to you when it's vertical. And this means that when we're driving and cycling and scoring, our box won't wobble because we'll be pressing into the hard stop. Now, in terms of the pivot itself, you can use metal chain or 9 millimeter width HDD5 belt. Either one works. We used belt, but teams have used chain in the past. And another key thing, which we kind of found out later, is that you want to use a high gear ratio off the motor to reduce backlash from the motor gearbox. So what this means is that the motor gearbox actually has, like GoBuilda Yellow Jackets have some internal backlash in their gearboxes. So it's around like 3 to 5 degrees, which can actually be pretty bad for when you're doing a pivot system because when you're extended, that 3 to 5 degrees is multiplied by a lot. Um, so what you can do is if you have a high gear ratio from the motor, for example, 1 to 10, then what that entails is that that 3 to 5 degrees gets reduced by a factor of 10. And so yeah, that's why it's important to have a high gear ratio off the motor. And also you want no backlash in your independent power transmission. So you want to have adjustable idlers because belt and chain can stretch over the course of a season. So yeah. In terms of pocketing the box tube, so some teams have ran pocketed box tube with such as us, and some teams have run pure aluminum tubes. There's pros and cons to each way. So the pros for pocketing a box tube is that it saves a little weight. For example, our box tube was 395 grams when pocketed and 559 grams when unpocketed. So a little more than 160 grams saved. And this is just the weight of the four individual tubes, not all of the bearings and stuff. But and other pros while pocketing Boxcube is that it's much easier to access strings on the inside when you have access holes through pocketing. But there's some issues with pocketing where if you pocket too aggressively, the face can deform slightly, which can lead to issues in regarding to bearing tolerances. So it's important to not pocket aggressively. Our team pocketed the first three stages, not our last stage, because it was our last stage was our last stage was is 0.5 inch, half an inch like wide, which is pretty small to pocket. But for this first stage, which was 2 inches, we actually 2 inches by 2 inches, we actually pocketed this a little too aggressively, and one of these struts bent a little because these have a lot of load when they're going onto them, which can lead to some issues. So in general, you just want to be safe when you're pocketing. And just some stats that you want to use 1/16 inch 6061 aluminum. Uh, when aluminum is in this like square format, like square tubing, it's actually really strong. You don't need to use 1/8 inch, 1/16 inch is good. And you want to pocket in an ISO grid fashion like these demonstrated here. There's a question in chat. Yeah, I think it was answered, but Boxtube is generally a little lighter than slides because of um, it's a lot more compact. That's part of the reason. And also slides to achieve like a general good amount of rigidity. Generally, you need two sets of linear slides, but for box tube, you just need one set of the box tube. And another reason for them being lighter is that the first stage in box tube, which is the heaviest, actually doesn't move. So this stage at the bottom will not move, but these three are the only stages that are actually moving when extending. Um, Now, the next topic which I'm going to be discussing is Boxtube inserts. So this is perhaps the most important part of Boxtube because it's really difficult to design good inserts that have good tolerances, because if your Boxtube inserts break often or they're not rigid or they don't have good tolerances, your Boxtube is just not going to be good. So there's two types of inserts in box tubes. There's inner inserts and outer inserts. So I'll start with the inner inserts. So the inner inserts go at the bottom of each tube like this. Let me get uh, they go at the bottom of each tube like this, and they have bearings on all four sides, which contact the tube that it's inside of, or the tube that's on the outside of it to ensure that it's like completely rigid. So some notes about the inner inserts. So we use fully 3D printed inserts. I would print them with high walls, high infill. If you can use a stronger material, that's also beneficial. So this is kind of the general structure of the insert. We found that it's better to use bearings with larger contact surfaces. So this is a bearing which has an 8 millimeter outer diameter and 4 millimeter width. We used to use 6 millimeter outer diameter bearings, but they had some issues with breaking. And you can see that we have one bearing on each side, and you need to make sure that this aligns with the pocketing on each tube if you're pocketing your tube, because the bearings have to go slide along that strut. And to constrain this bearing, what you can do is you can use threaded rods. Oh, sorry. You can kind of see in this image, we have threaded rods which constrain each bearing. And what
during
we
the
do is you
virus
can just
period. And first thing that we wanted to do was detect samples of summers both using
um
our AI model. Then we map
sorry,
samples onto a 2D plane.
I'm not okay. I'll just
Sorry
continue.
about
So
that, guys.
it's okay. So to what you can do is you undersize these holes in the 3D print a little, so you can essentially screw in these threaded rods. And you can also call them a kind of a long set screw instead of a threaded rod. And you can get these from Amazon, these long set screws that have Allen key ends on, like hex key ends on the end. You screw them into the 3D print, and it's completely okay to screw them into the 3D print. But if you're worried about them loosening over time, you can just add a drop of super glue. And we have these shims built into these bearing inserts so that the bearing spins perfectly smoothly without any friction. Now, perhaps the most important part, which I'm going to talk about, is tolerancing these inserts. So, if you just design everything to be perfectly tangent in CAD, it's not going to work the first try. You're going to find that either the tube is, when you design this and try fitting it onto the next tube in real life, either it's not going to fit or it's going to be, there's going to be play in the stages. There's going to be play between the tubes, which causes the tube to not be rigid. So what I recommend doing is design these inserts to be configurable. So let's say you're using Onshape, design them to be configurable so you can adjust these tolerances in terms of how much the bearing goes into the next aluminum face. And that way, if you quickly iterate these, you can design the inserts such that they have very like almost zero play, which means that they should not be able to move when each tube is inside of each other, but also slide smoothly. Again, you don't want there to be any like side to side or front to back movement in these bearings when it's in the tube. So you're gonna have to print out at least 4 or 5 copies of each insert for each tube. So that's one of the biggest struggles of Boxtube that teams don't really know about when they're going into it. And then another thing is you want to have at the bottom of each tube, you need tie-off points for each string, which we'll talk more about later since we're doing cascade stringing. But what we did is we have these screws with these nut captures, which is where the string can tie off at each point. And again, if you have any questions, just ask while I'm talking. So now onto the outer inserts. So the outer inserts are like the are almost take more load than the bottom inserts. And that's why we've kind of designed these unique inserts, which we feel are almost pretty good for FTC. So the outer inserts go on each side of the tubes and they constrain the inner tube as such, as you can see here. And what we recommend doing for these outer inserts is to have this design which uses aluminum inserts integrated with a 3D print backing. So one of the biggest difficulties for designing a box tube is finding a strong way to mount these side bearings. So these are the side bearings which constrain the tubes side to side. So what we decided on for our V2 box tube is we have these 1/8 inch aluminum plates, and these are super rigid. And this 3D print backing goes on with this dowel pin and a bearing for the side for constraining the tube side to side. And what you'll notice is that since this 3D print and the aluminum plate are screwed in together, they're actually super rigidly mounted that there's almost no load on the 3D print. So almost all the load goes on the aluminum plate, which it can handle. And what you're going to notice is that tolerancing these inserts is going to be another big thing which I'm going to talk about, and one of the biggest struggles with FTC with Boxtube. So what we did is we ordered a from Fabrics a bunch of these aluminum plates with different tolerances. These may look similar, but the tolerance values ranged from zero point 0.0 to 0.5 millimeters in. So we're adjusting the tolerances in ticks of 0.1 millimeters. And we first tried out different ones of these inserts to tune the front and back tolerance. So front and back is this way. And then once we've designed the optimal front and back tolerance for these bearings to contact these tubes, then you can adjust the side to side tolerance by adjusting this 3D print. And again, if you can use configurable part studios and Onshape, that's really beneficial. Now, some more details on the inserts itself. It's really good to use bigger bearings because the bigger bearings can take a lot more load. Um, you can see for these front and back bearings, we have a screw running across with bearings here and 3D print spacers, as well as a V-groove in the middle for stringing. And there's shims on each side, which you can't see. And then the side bearing, as I talked about earlier, we have these dowel pins. And these dowel pins, you might be wondering how are they constrained, but they're actually fully constrained. Side to side, they contact the aluminum face of this aluminum piece front end for backwards, they're pressed in by the 3D print, and on the inside, they're constrained via the face of the tube. So these bearings are actually fully constrained. And you can also use shims here so that they don't contact the sides of the 3D print. And another thing that I wanted to talk about quickly is wire management. So there's what we use this year is the loop method for wire management. We have these zip tie off points. You can see them here and here, and you can just slide a zip tie through here and zip tie the a cable sleeve into here, and that'll essentially allow you to like wire your mechanism by having loops of cable sleeve on each stage. So again, just to summarize these outer inserts, you want to use bigger bearings on every face so that you can really have strong contact faces and really low play and really high rigidity. And we have V grooves for the stringing as well as fully constrained on every piece. We have 3D print spacers and we have these dowel pin assemblies for the side bearings. So hopefully that makes sense for the outer inserts. Now, I'll pass it on to Kanishka to talk about stringing.
Yeah, so for Boxtube stringing, so Boxtube is generally cascade strung because you can't have V grooves on the bottom of each stage, and that means that there's n number of extension strings, and when there's n number of stages, so the amount of extension strings you have is the same as the amount of stages. All three stages extend simultaneously, so they all extend at the same time, and all three and so this changes the effective RPM as compared to something like continuous stringing because you have less torque but more speed. And when calculating like your optimal ratio, you should keep this in mind that there's going to be n times as little torque and n times as much speed. So adjust your ratio accordingly. So look up just on YouTube, look up for knotting all of your stringing. This is just stringing in general. Look up fishing knots, and they're just the best knots you can find for stringing in general. And they're very strong. Don't use just regular square knots; they will come loose. And in Boxtube, if your knots come loose, then your Boxtube strings will be of different length, and that means that because it's cascade, it won't fully retract and it won't fully extend. So that will be an issue for you. Use a large zip tie for tensioning. You can see the large black zip tie in the bottom right, and that just allows you to easily adjust the tension of your continuous retraction string because you can easily open or close the zip tie more or less to make it more or less tension. And that also kind of doubles as our spring, where we didn't want to use a regular spring because it could easily catch on stuff, especially on the outside. So using a zip tie just because it's very large and flexible kind of doubles as that. Now make sure, especially your continuous retraction string, make sure that it's parallel with your Boxtube, because if it's not, it will cause the string to loosen. So it'll be on hypotenuse compared to the Boxtube. So as it extends and retracts, the ratio won't exactly be 3-to-1. And your spool is 3-to-1, meaning that it'll loosen. The big thing about anything loosening is if it loosens, you will likely de-string. So this picture up here is actually what happens when you lose tension. The string comes off your V groove and it gets stuck on the side. So that's just not good. If you have a bearing shield, it can also get stuck in the edge of the shield. So yeah. And your extension is continuous, but your extension is cascade, but your retraction is continuous. So that means that your retraction should be n times as large as your extension. For us, it's 3 stages, so our retraction is 3 times as large as extension. Now, in terms of maintenance and making sure your Boxtube actually runs well, so this kind of goes without saying, but make sure your Boxtube is clean. If your Boxtube isn't clean and you have a bunch of dirt on the outside, then of course it's going to have a lot of friction. It won't run smoothly, And just through general use on a field, it collects a lot of dirt. So make sure you thoroughly clean it. Aluminum can just be cleaned regularly with soap and water. The outside is fairly easy to clean, but the inside may be difficult to clean. So you can clean it like from the back of the box tube, like the bottom of it, or you can clean using the pocketing. You can like reach inside and clean it. And additionally, make sure your box tube is always well lubricated. Almost all lubricants work, like just WD-40, and this stops the bearings from shaving off material from the tubes, and that can also cause a lot of friction, and it just makes it run much faster and smoother. Like it, especially like before a competition, both of these things you should be doing. And that's about all for box tube maintenance. Thank you for listening.
Thank you guys for presenting about Boxtube.
Any questions anybody has? No? Okay.
If there's any questions in the chat, I think y'all can answer this in the chat while we go on to the next presenter.